Today we're going to be reading Chapter 2 in Life of a Star, so you might want to have that book out and follow along as I read. So Chapter 2 is main sequence of a star. So we're going to learn and think about the characteristics of the sequence of a star, like its life. We learned in Chapter 1 how it was born, and so now we're going to learn about its life sequence. A star's mass decides whether it moves on to the next stage. Mass also controls the length of a star's life and how it will die. For example, not all protostars go on to become true stars. A protostar cannot begin nuclear fusion without enough mass or heat. Without nuclear fusion, a protostar becomes a brown dwarf star. This star is a cold mass of debris. It is not hot enough or heavy enough to make its own light. Other protostars are large enough and hot enough to enter the next stage. This is known as the main sequence stage. During this stage, nuclear fusion happens continuously in a star's core. The star gives off rays of light and energy. A star remains in this stage for most of its life. A main sequence star has a core temperature of millions of degrees. This causes the star to glow. The star also reaches a state of stable equilibrium. This means the gas pressure pushing outward from the core is equal to the star's inward pull of gravity. So that's stable equilibrium, when what's pushing outward is the same as the gravitational pull, because all objects have a gravitational pull that pulls everything to their center. So it's a stable equilibrium, and if you think about that word equilibrium, you hear the word equal in there. So the outward force and the gravitational pull are the same or equal. As long as the star is balanced, it will remain a main sequence star. The closest main sequence star to Earth is the sun. So that's the stage of life that our sun is in. It's in its main sequence stage, and that's the stage that it stays in for most of its life. So, when we last read this book, Chapter 1, we talked about, will the star ever die? Will the sun ever die? And yes, it will, because it's a star. But according to this, it sounds like we'll have some warning, because this stage, the main sequence stage, is the stage it stays in for most of its life. So when it enters another stage, it must start to die. I don't know. That's an inference I have. Probably when we read the rest of the book, we'll find out. We have this caption here. It says, nuclear fusion creates very light, non-electric charges called neutrons. By studying these neutrons, scientists learn about fusion inside the stars. And the picture on page 13 says, in this picture of a brown dwarf, scientists are unsure. It's hard to spot a brown dwarf. It often looks the same as a large planet. Interesting. A brown dwarf looks the same. A star is looking the same as a planet. All right, parts of a star. The sun is a medium-sized star. Astronomers study the sun because it is only about 93 million miles away. Other main sequence stars are billions or even trillions of miles away and hard to see clearly. So in yesterday's lab, we talked about is the sun the brightest and biggest star in our solar system? And it's not. It says the sun is a medium-sized star. So why does the sun look so big and big and bright to us? Because it's closer. Even though it's 93 million miles away, it's still closer than other stars. The sun has the same parts as all main sequence stars. All main sequence stars have a core. This is where the sun makes its energy. Core's in the middle. Radiative? I'm not sure what that word is. Radiative zone. This zone is outside the core. Here, energy moves in the form of photons. Photons are a type of radiation. Convective zone. This layer is less dense and cooler than the radiative zone. Here, hot gas currents from the radiative zone carry photons toward the surface. These currents make the surface look like it is boiling. Photosphere. This is the star's atmosphere. It emits light. Chromosphere. A hot region where shock waves from the photosphere produce millions of tiny spikes of hot gas called spicules. Spicules. That's a new word. Those are tiny spikes of hot gas. And then the corona. This is the layer of gas around the star. It is much hotter here than the core. The temperature of the corona averages 3.6 million degrees Fahrenheit. So the outer edge of the star, the corona, is actually hotter than the inner core is. On page 14, we have a picture that says, solar flares are sudden violent explosions on the sun. Over time, a solar flare's radiation and particles reach Earth's magnetic field. Then the particles can disrupt electrical systems, such as power grids on Earth. On September 23rd, 2000, we had the approximate size of Earth, and it says sunspots are dark, cool areas on the photosphere. Magnetic fields break through the surface of the sun and cause sunspots. So that is a blown up picture there. That yellow and orangish picture is a blown up picture of sunspots on the sun. And you can see that's just one little tiny area of the sun. And you can see how small the Earth is in comparison. Historical perspective. In 1543, Polish astronomer Nicholas Copernicus became the first to declare that Earth traveled around the sun. However, the Roman Catholic Church declared that the sun revolved around the Earth. To disagree with the church belief was a crime. In 1609, Italian Galileo Galilei built a telescope and observed the motions of planets in the solar system. He discovered that Copernicus was right. Galileo was arrested when he disagreed with the church. He spent the rest of his life under house arrest. So, a long time ago, they thought the sun was what's revolving around the Earth. But because of Galileo and his telescope, we now know and believe that the Earth and all the planets revolve around the sun, which was also in our demonstration yesterday on the lab. How long a star remains in main sequence depends on its mass and amount of fuel. Very large stars are much hotter and brighter than smaller stars, like our sun. Yet stars with greater mass need more energy to stay in equilibrium. Very large stars burn much more quickly than medium stars and small stars. This means that the larger a star is, the shorter its life would be. You might think that the larger a star is, the longer its life is because it has so much mass, but because it requires so much fuel to keep burning, it actually has a shorter lifespan. So I can connect that to dogs. You might be thinking, how in the world can you connect this to dogs, Miss Bridges? Well, did you know that larger breed dogs have a shorter lifespan? For example, and I know this because I had a German Shepherd Shepherd's lifespan is only about 10 to 12 years on average. They're not saying that they can't live longer than that or sometimes shorter. But the larger the breed, the shorter their life expectancy. And so that is very similar and how a star is. The larger the star, the shorter the lifespan. A star of this size will have, I missed the spot. One of the most massive stars known today is Eta Carina. Eta Carina. Eta Carina is highly unstable. Chunks of the star's outer layers often blast off into space. So yesterday we were talking about that there were stars bigger than the sun, but I didn't know any. And now I do. Eta Carina. A star of this size will have a very short life. Astronomers predict that this star will live only 1 million years. 1 million years is a short life? Wow. A star spends about 90% of its life in the main sequence stage. This can be millions or billions of years. Over time, a star runs out of fuel. When this happens, a star enters its next life stage. So when it runs out of fuel is when it goes to the next stage. On page 16, it says, in the mid-1800s, Eta Carina was one of the brightest stars in the evening sky. Today, it cannot be seen without a telescope. So why was it so bright then, but not anymore? It's running out of fuel. Astronomers predict the length of a star's life by comparing it to the mass and luminosity of the sun. So we can see a chart there, the mass and the luminosity, and how many years it will live. And it also has a little side note that the E is for exponent, and you should be familiar with what that E is, what an exponent is. That's a math. That's a connection to math. So in the first part where it says 3e6, that's 3 to the 6th power. Okay, so that's 3 times 3 times 3 times 3 times 3 times 3. That was 6 threes. Math matters. Scientists use a special measurement called a light year for huge distances. A light year is the distance that light rays travel in 1 year. That's equal to about 5.9 trillion miles. Astronomers need this large of a measurement since stars are so far away. For example, the distance between Earth and the next closest star after the Sun, Proxima Centauri, is about 4.2 light years. So when that star dies, we'll see its light for another 4.2 years. Interesting, right? How long it takes light to travel. And that is actually the end of chapter 2, because chapter 3 is the next life stage, which is the death of the star. And so we'll see what happens when a star enters that stage of its life. Hopefully you have learned some characteristics of the main stage of a star's life. We learn that the bigger the star is, the shorter its life expectancy. We learn that there are bigger and brighter stars in a galaxy than our sun. Our sun is just the closest to us. If you have any questions about what we read today, please send me an email.